So I'm Nir, and I'm going to tell you about virtual gray box obfuscation for general circuits. And this is joint work with B-Canetti, Yael, Kalai, and Omer, Paneth. OK, so we heard about ideal obfuscation and the virtual black box definition, which is probably the most intuitive and expressive definition that we have for obfuscation. It essentially says that whatever an efficient adversary can learn, given an obfuscated circuit, should also be learnable by an efficient simulator that can only run this circuit as a black box. Now, unfortunately, as we heard, we mostly have impossibilities for this strong notion and very few positive results. Now, for a long while, we also had a matching picture from the perspective of constructions who basically had no candidates at all. Again, except for very simple stuff. But as you already know by now, things dramatically changed last year. And now we have a candidate obfuscator for all circuits based on multilinear graded encodings. And of course, that the first OK. So the first question that is raised here is, of course, what kind of security does this candidate have? So we know that it cannot be virtual black box, it cannot be VBB for all circuits, so what can it be? And the notion that was suggested as a benchmark is Indistinguishability Obfuscation, or IO for short, that essentially says that the obfuscations of two circuits that compute the same function should be indistinguishable. Now, perhaps the main reason that this notion was chosen is that we simply don't have any impossibilities for this notion. So you could in particular assume that our candidate obfuscators satisfies IO. Okay. But this is, of course, only a first step. And ever since, there's been attempts to increase our confidence in this candidate, either in ideal algebraic models, where it can be shown secure, or also in the plane model under more concrete assumptions on the underlying graded encodings, like semantic security and subgroup elimination that we heard about yesterday. Now, trying to strengthen our confidence in the fact that this candidate is IO is very well motivated, especially given the tremendous applications that IO turns out to have. But in the same time, we should also ask ourselves whether IO is really the best thing that we can get here. Perhaps this candidate can satisfy more. Now, this is kind of a tricky question, because formally, actually, we do know that IO obfuscation is in some sense the best possible. It hides whatever the best possible obfuscator would. So perhaps we need to rephrase the question and ask, how good is the best possible? Because the thing is that as an obfuscation notion per se, it's not really clear what IO hides. And whenever we use it, or typically, we have to work kind of hard. And it may very well not suffice for many of the applications of the more intuitive VBB notion. So this motivates us to look for more expressive notions than IO, and hopefully try to achieve such notions, if we can, for as large classes of circuits as possible and under similar assumptions. And in this work, we focus on a particular such notion, which is virtual gray box obfuscation, or VGB for short. So let me tell you what's VGB. So remember that in VBB, what we require is that for any efficient adversary, we have an efficient simulator that can learn the same things, just given black box access. The virtual gray box definition relaxes this. It relaxes this by allowing the simulator to be computationally unbounded, but we're still going to limit the number of oracle queries that it can make to the circuit. So this is the VGB definition, and let's try to get a sense of what it means. So one thing that we can surely say is that it lies somewhere between IO and VBB. Actually, IO is known to be equivalent to a simulation definition where the simulator is completely unbounded and also gets an infinite number of oracle queries. Now, for what functions is VGB meaningful? So it really depends on how learnable they are. Are they learnable by an unbounded learner with a polynomial number of queries? This affects the question. So for example, for point functions that accept a single random point, then VGB is actually very meaningful. It is known to be as meaningful as VBB, whereas for IO, we don't really know what IO hides in this case. But if we go to functions of a more cryptographic nature, like say pseudorandom functions, then whereas VBB definitely guarantees something and would have great applications, it's not always clear what VGB will give. Okay? Now, while this may seem like a serious limitation, it's also good news in some sense, because this is exactly what makes VGB escape the impossibilities that we have on VBB, like those that Omer talked about. And in fact, we do not have any impossibilities at all for this VGB notion for circuits. So a natural question is, perhaps we can show that our candidate obfuscator is even VGB. Okay. So let me tell you what we show. So the starting point is going to be a result by Pass-Seth et al. That we heard about yesterday that shows that semantically secure graded encodings imply I/O. And our first result is that under a slight strengthening of this assumption of semantic security that we will call semantic security star, we can get not only I/O, but also VGB. Okay? But here it's only going to be VGB for classes of circuits in NC1. Now, we don't really know whether semantic security is necessary for I/O, and you can hope that since VGB seems stronger, perhaps it's necessary for VGB, but we don't quite know that. But what we do show is that a restriction of semantic security to something that is known as jigsaw puzzles, rather than for graded encodings, is necessary for VGB, at least if you want VGB for all circuits. And it still has the same applications. Okay, so there is some tightness here, but there's also some gap. Now, another interesting thing is that using our techniques, we can actually show that for some classes of functions with specific properties, you can actually also get virtual black box obfuscation, not only VGB. And examples include Hamming balls, constant dimension subspaces, and conjunctions, which are things that we did not know to be VBB obfuscatable before. In the paper, we give more careful characterization of the required properties. And another interesting thing is that we actually get one unified proof for all the VBB obfuscators that we have, both the new ones and also the existing ones in the literature. Okay, so in the remaining time, let me tell you a little bit about our approach. So we're going to follow a pretty familiar paradigm in crypto, which is to try and go from an indistinguishability definition to a simulation definition. Okay, in our case, the VGB definition. And we know that this paradigm has been pretty successful. Perhaps the most famous example is semantic security, and we'd like to try and apply it here. The question is, of course, what kind of indistinguishability notion would imply this simulation-based VGB? It would be great if IO implies VGB, but we don't know how to show that. What we're going to show is that VGB is actually equivalent to a strong notion of IO, which we'll simply call strong IO. Okay? And then in the second step, we show that this strong IO notion is implied by semantically secure graded encoding. So what is this notion of strong IO? Let me tell you. So remember that in standard IO, we require indistinguishability for obfuscations of any two circuits that on each input completely agree with each other. Now in strong IO, instead of thinking about pairs of circuits, we're going to think about pairs of circuit distributions. Okay? And we will require that indistinguishability holds if for every input, when you sample two random circuits from these families, then with overwhelming probability, they agree with each other. Okay? So this really has the flavor of IO. But we can actually show VGB from this thing. And the interesting direction is really showing how strong I/O implies VGB. The direction in the other way is pretty direct. Also showing that semantic security implies strong indistinguishability is pretty direct. I will say a word, though, about what is this star, what is this strengthening of semantic security that we need here. So very, very roughly, semantic security is an assumption about multilinear graded encodings. And a bit oversimplifying things, it says that for any two distributions on vectors of ring elements and some corresponding multilinearity levels, we want their encodings to be computationally indistinguishable if you cannot distinguish them in an ideal world where you can only do algebraic manipulations and a polynomial number of zero tests. Okay? So this is semantic security, and Pass-Seth, I'll show how to get I/O from this. But actually, for them, it suffices that semantic security holds only for efficiently sampleable distributions. But this turns out to be insufficient for VGB. In order to get strong I/O and VGB, we will also need semantic security to hold for arbitrary distributions. So this is the star here. OK, so in the rest of the time that we have, I want to sketch how we exactly move from strong I/O to VGB. And remember that our goal here is to construct a simulator that can simulate the output bit of any adversary that gets an obfuscation of some circuit C, while the simulator is going to be unbounded and get a polynomial number of queries to the circuit C. OK, so what is going to be our high-level simulation strategy? Let's imagine that the circuits in our class are these points in space, and the circuit C is one of these points. And in the first step, our simulator is going to try and naively learn the circuit C. So how will it do so? It's going to use its unbounded power to find an input X that significantly splits the set of circuits, and then it will simply ask its oracle C on this point X and disqualify many of the candidates, okay, a noticeable fraction of the candidates. And it will continue to do so using its unbounded power every time disqualifying a noticeable fraction. And this goes on polynomially many times until it gets stuck. Okay? And what does it mean that it gets stuck? It essentially means that all the circuits in the remaining set are very concentrated around some specific functions. So for example, maybe all these circuits are just point functions, many random point functions, and we're concentrated just around the all zero functions. Now, when we get stuck, there are two basic options. Okay? One option, this is actually the good option, is that the adversary, somewhat like the simulator, also cannot tell an obfuscation of our circuit C from an obfuscation of something random in this set. Here, simulation would be easy. We would simply run the adversary on an obfuscation of something random. Okay. But it may also very well be that the adversary may have some information, some hard-coded information about the circuit C. So for example, if the circuit C is a point function, maybe the adversary knows the point or a small set that contains the point, and this will allow it to distinguish obfuscations of the circuit from an obfuscation of something random. Now, in this case, our simulator will have to find a way to somehow extract from the adversary this meaningful information. It has unbounded power in order to do this extraction, but only a polynomial number of queries. OK, and once it will do this extraction, it will use it again in order to kind of reduce the set and continue in the same manner. OK, so now really what is left is to talk about what kind of extraction can we do and how the strong I/O fits in. OK, so what we're going to do is basically think about what we call the distinguishable circuits in this set. Okay, and these are the circuits that are basically exactly those that the adversary can distinguish from random circuits in this set when, of course, they're obfuscated. Okay, we're going to call this set D, and these are the red dots in our set. And our goal is going to be to get convinced that either our circuit is not one of these distinguishable elements, distinguishable circuits, in which case we already know how to simulate, right? We said we just obfuscate something random and run the adversary. Or this is what we want to extract from the adversary. We want to find an X that separates the circuit C from the majority in the set, from this function that everything is concentrated around. Okay? Because again, if we can do that, then again, we can disqualify many of the candidates and continue on. Okay, so how are we going to achieve this goal? So you can guess we're going to use strong I/O, and let me tell you how. So we show the following claim. What we show is that there exists a small set of inputs that can separate all of those distinguishable sets from the majority. Okay? Now, if there's such a small set of inputs, we can definitely use it to continue in the simulation because the unbounded simulator can simply, again, use its power to find it. Okay? And then it would query the circuit C on all of these input X and see if the circuit C, either the circuit C agrees on all these inputs with the majority, which would simply mean that it's not one of the distinguishable circuits, or we have separated C from the majority and achieved our goal. Okay. Now, I'm not going to prove this claim, but I will give you the intuition, because the intuition is exactly strong I/O. So the point is that if there's no such small set, then this basically means that the distinguishable circuits themselves are kind of very much concentrated around the same majority, around the same function. And in this case, we can actually split our set into two distributions, which are both concentrated around the same function, around this majority. This means that for any input, if we choose two random circuits in these sets, then with overwhelming probability, they agree with this majority and thus also with each other. On the other hand, we know by definition of the distinguishable circuits that if you now obfuscate something random here and obfuscate something random here, the adversary can tell them apart. Okay, this is exactly their definition. And this contradicts strong I/O. This is exactly a contradiction to strong I/O. Okay, so this is the rough intuition. And there are actually a couple of interesting open questions about strong I/O and VGB, but I see that I'm out of time. I'll be happy to discuss them offline, and I'll end here. Thank you.